So it's a great pleasure to have Shuo Qin.
Yes.
I'm not sure if I pronounced it very well, but he from the Beijing Institute of Mathematical Sciences and Applications. He will be talking about elephant random walk.
Okay. Thanks, George, for the introduction, and I'm very happy to be invited to this wonderful program. So today I'm going to talk about elephant random walk and constant, a universal constant 1/2 hidden in this model. So let's first look at the definition of elephant random walk. So now we're looking at two-dimensional elephant random walk. So the elephant start at a region, and let's assume that the first step is to your right. So then at each time step, the elephant randomly choose one of the previous steps. For example, here the elephant has made 11 steps. It uniformly choose one previous step. Let's say the step in red. Then with parameter p is a parameter between 0 and 1. The elephant repeat this step. Otherwise, the elephant choose one of the 3 remaining directions uniformly. So each direction has probability 1 minus p divided by 3. So this is the definition for two-dimensional elephant random walk. One can also define it actually in any dimension in ZD. So in ZD, you first choose the previous step with probability p repeated. Otherwise, you choose one of the 2d minus 1 directions, each with probability 1 minus p divided by 2t minus 1. So a special case is that when p equals 1 over 2d, for example, in dimension 2, when p equals 1/4, actually it's just a simple random walk. No matter which direction you choose, each direction of this 4, E1 minus E1, E2 minus E2, all has the equal probability 1/4. So it's just a simple random walk.
It looks like the steps are not necessarily of length 1, right? Or is it?
Sorry?
It looks like you have big steps, but I think you mean just the consecutive, right?
Yes.
Can I just understand the construction?
Yeah.
So if you are at some point in the grid,
Yeah.
you uniformly pick one of the previous directions that you picked, uniformly from the previous path that you have.
Yes.
With probability p, you use that one, and with the rest, you take any other direction.
Yes. Okay, so one of the basic questions on this model is whether this is recurrent and transient. But actually, this is a non-Markovian random walk. So one need to define what the recurrence and the transience mean. So, but actually for this model, we can use the usual Markov chain definition. So we say elephant random walk is recurrent if every site in this ZD lattice is weighted infinitely often. If we say it's transient, if it goes to infinity almost surely, or every site is weighted finitely often almost surely. So this question has been open for a few years, and Professor Rang Botois made a conjecture that in dimension identity 3, it should behave like a simple random walk. It's transient. And in dimension 2, he thought it's somehow a challenging problem because dimension 2 is it's a critical dimension even for simple random walk, and in this case, it's mono-Markovian. So the main result is that in dimension identity 3 is transient. In dimension 2, there is a phase transition between recurrence and transience. When p less than 5/8 is recurrent. When p is at least 5/8, is transient. But it has been proved that in dimension 1, it has been proved that there is also a phase transition between recurrence and transience. But that's at p equals 3/4. So when p is less than or equal to 3/4, it's recurrent. Otherwise, it's transient. So there's a difference between dimension 2 and dimension 1. So at the criticality, in dimension 2, it's transient, but in dimension 1, it's recurrent. So let me briefly talk about the history of.
Are for dimension one, it's always recurrent basically.
That's one half, right? One half is the simple random walk in dimension one. One half in dimension one half. When p equals one half is a simple random walk. Yeah.
For anything else, I guess you drift apart. So
yeah, so you should have basically when let's say in one dimension one, you made imagine that you have made many steps to the right, but fewer steps to the left. Yeah. So now you are on the right hand side of the origin. When p is large, basically you have a drift to the right, but it's not from. It's not an outer external field. You are driven by your memory. Yeah. This is why it's a reinforcement. So this parameter p is called memory parameter, or somehow it's called a reinforcement parameter. So it's called the elephant random walk because there is saying that elephant has a good memory or long memory. It was introduced by two physicists about 20 years ago. Initially, it was introduced, it was defined only in dimension one. So in dimension one, you choose a step with priority p, you repeat this step. Otherwise, you go to the opposite direction. So in dimension one, there is a phase transition as 3/4. So when p is less than 3/4, it's called the subcritical regime. When p equals 3/4, it's called the critical regime. In these two regimes, there are certain kind of central limit theory and the log iterator logarithm. So when p equals one half is just the usual central limit theory. It's a usual OLIL. But at the criticality, so you have a very unusual growth rate. The normalization constant here is n times log n. Here is n times log n times log 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 n. Yeah. Yeah, but here you have I only wrote down the limit soup, but basically for limit inf it will be -1. So this shows that for p less than or equal to 3/4, the limit soup and the limit inf of this work are equal to infinity and minus infinity. So this shows that it's recurrent when p is less than or equal to 3/4. But when p is greater than 3/4, this is called the supercritical region. So there is a almost sure convergence result. So Sn divided by n to 2p minus 1 converge to some random variable, non-degenerate random variable. And one can deduce from Bauer and Bortwas work that this limit is actually almost surely non-zero. So basically you have a limiting direction. You escape from one side. So this shows that when p greater than 1/3, it's transient.
Can they compute the moments of the W1?
Yes, that basically they compute the first 4 moments. Yeah. Yeah, then one can deduce that W1 is non-Gaussian. Yeah. So then we talk about the d-dimensional elephant random walk. Those results can be generalized to higher dimension case. So in dimension 1, the criticality is p1 equals 3/4. Actually, in any dimension, there is a criticality pd, which equals 2d plus 1 divided by 4d. When p is less than 2pd or equals to pd, there are certain kind of central limit theory and AIL. But when p is greater than pd, there is an almost sure convergence result. For example, when p is greater than pd, s divided by n to the alpha will converge to some non-degenerate random vector, d-dimensional random vector. And actually it's a non-degenerate random vector. Okay, so then we can show that just like in dimension 1, where the random vector is almost surely not a zero vector, so there will be a limiting direction. This shows that when p is greater than pd, is transient. And actually, we can even show that when p is less than or equal to pd, there is a limit. There's no limiting direction. So Sn divided by its distance to the origin does not have a limit almost surely. So let's look at okay. So let's look at the two simulation results for two-dimensional elephant random walks. So in each figure, I plot 4 independent two-dimensional shapes. So the left-hand side is subcritical region when p is less than 5 or 8, 0.625. So it behaves like a simple random walk. This is no limiting direction. And when p is greater than the criticality 5 or 8, you are somehow stretch the sample path becomes more and more straight. So there is a limiting direction. So basically, if we are curious, we also plot the simulation result for the criticality. So, but one cannot say too much for this case from the simulation result. So if you look at the trajectory in blue, there is no limiting direction. But you look at the trajectory in, like, for example, in red, you may have a limiting direction. But actually, one can rigorously prove that there is no limiting direction at the criticality. So what I will mention that in dimension 2, there is a phase transition at 5 or 8 between recurrence and transience. Indeed, this is a double phase transition. Recurrence and transience are property of a radial component. But for angular component, actually there is also limiting direction. There is also phase transition. If p is, but there is a different. They are different. So when p is less than or equal to 5 or 8, there is low limiting direction. But for the recurrence and transience, when p is less than 5 or 8, it's recurrent. Okay, so actually now we're trying to generalize this model. So we can, okay, here I denote n of v, the empirical measure of the steps. So let's count how many steps you have made to each possible direction until time n. So then recall that I just define a parameter alpha by this formula. So actually one can rewrite the transition probability for the next step by using this. So the left-hand side is just the definition for elephant random walk. So you first sample and previous step, then you repeat it according using with probability p. Otherwise, you made such a step, you have to sample a different step, and you choose this from the remaining 2D minus 1 steps. So left-hand side is just a definition for elephant random walk, the previous definition. But actually, using this alpha, you can rewrite this transition probability that it actually equals this. But when alpha is, so basically we'll give a second definition for the elephant random walk using a new parameter alpha. So when alpha is non-negative, basically it has a clear probabilistic meaning. So basically this shows that we can define this like we can define elephant like this. So with probability alpha, we sample or we choose one of previous steps uniformly. Otherwise, with probability 1 minus alpha, we choose one of the directions from the 2D directions uniformly chosen. So this one is just a probability measure on this set. So actually, we can replace this uniform distribution on this set by a general distribution in RD. So this leads us to the definition of the so-called step reinforcement walk. So it's definitely, I think it's even simpler. So let's say the first step you sample mu. Mu is a probability measure on RD. The first step you sample from mu, and then subsequently you with probability alpha you repeat one of the previous steps uniformly at random. With probability 1 minus alpha, you just made an independent increments, independent of the past, sampled from mu. Right. So then they will be called a step reinforcement walk with parameter alpha and step distribution mu. So such a algorithm dates back to 1955. So where Simon introduced the algorithm to explain the appearance of power law in a wide range of empirical data. So, but in his paper, he used words instead of steps. So imagine that you are writing a long book. For the k plus first word, with probability alpha, you choose one of the word from from the first k first words. With probability 1 alpha, it's a new word, different from all the previous words. So this somehow corresponds to the case when mu is non-atomic. You can or correspond to the polar model with innovation. Yeah, you can always introduce a new type of word. Then you study the proportion of the words which has been used. The book is finished until the length reach a very large n. Then you compute the proportion of the words which has been used exactly once, twice, 3 times. Basically, you compute the number of times has been used once, then divide by n. Then when n goes to infinity, those proportions will converge to the so-called U or Simon distribution. Okay. So let's look at a few examples. So when mu is discrete, one can write the transition probability as this. So basically, when alpha equals 0, so basically there is no reinforcement. You always sample steps from mu independently. So basically, the Sn will become the sum of IID random variables. It becomes the classical random walk. So if mu is uniform on the 2D directions, we have shown that your second formulation of elephant random walk is actually is a d-dimensional elephant random walk. Now, we previously define alpha by in terms of p. Here we can write p using alpha. So I just want to mention that when p equals pd, if and only if alpha equals 1/2. So here we saw the constant 1/2 here, right? So if mu is a somehow stable distribution with 0 drift, this model is called the shark random swing. Yeah, I don't know. Maybe it's because maybe you have some more freedom to. Yeah, you can have a long jumps. So each steps you move very fast. Or anyway, yeah. So this is called the another animal here. Yeah. So when p when alpha is less than 1/2. Similarly, there is a certain kind of central limit theory, and actually one can Bothwa show that there is they established the invariance principle in dimension 1. So if the second moment exists, then this so this one will convert to so-called noise reinforced Brownian motion. It's going by this. So I'm not studying SDE, but if you are interested, I also list. Also, we can also define the noise reinforced Brownian motion using SDE. So it's the solution of this one. Then Bartinge and Russell Ortiz extended this result to the critical case. So just like elephant random walk, for alpha less than 1/2 and equals 1/2, we also have a central limit theory or even invariance principle. And Hu and Zhang established a strong invariance principle. So we're not going to use those results in this talk, but I think I should mention this because. So, but I'm going to use the result for when p is greater than when alpha is greater than 1/2. So anyway, for any alpha, there is a strong law of large numbers. So when the first moment exists, then Sn divided by n will convert to. So mu bar is the expectation of mu. Then when alpha is greater than 1/2, then almost surely, and the Sn this normalized process will convert to W almost surely ending L2. So, and W is also non-degenerate. So now we focus on the case when mu is a distribution on ZD. Just like before, we say that a stable reinforcement work is recurrent if every vertex in this R. This set script R is actually all the vertices that are reachable for this random walk. Then if every site in this set R is visited infinitely often, almost surely we say it's recurrent. If it goes to infinity, we say that it's transient. So now we just like the simple, that's like the classical random walk. We impose some moments assumption on the distribution, on the stable distribution mu. So here so non-degenerate is trivial. Otherwise, we will always make a same step. We say it's centered because if it's non-centered, using the low large numbers, it will goes to infinity almost surely. So that's why we assume that is centered. So the main result is this. So under the second moment assumption, for any alpha greater than 1/2 is transient. And this assumption is also enough for the recurrence in dimension 1 when alpha is less than or equals to 1/2. But for higher dimension, I impose a slightly stronger assumption. That's a 2 plus delta moments assumption. But delta is any positive constant, so it's a little bit stronger than second moment assumption. So under this assumption, S is recurrent if in dimension 2, S is recurrent if alpha less than 1/2. In higher dimension, it's always transient for any alpha. At the critical dimension 2, at the criticality 1/2, I impose an even stronger assumption, the force moment assumption. So under the force moment assumption is transient. So it will be even clearer to look at those figures. So here under the 2 plus delta moment assumption, in dimension 1 and dimension 2, actually in dimension 1 only needs the second moment assumption. So when alpha less than 1/2 is recurrent, the limit sup of log S divided by log N actually equals 1/2. But the limit does not exist. But when alpha greater than 1/2, the limit exists. So actually we can even have an estimate on the skip rate. And for higher dimension, it's always transient for any alpha between 0 and 1. And one can also show that there is actually in any dimension there is a phase transition. Even one can say that it's transient. But if you look at the escape rate, there's a phase transition at 1/2. So actually one can also consider elephant random walk on more general graphs. The next question was raised to me when I defended my thesis. So one can in two-dimensional case, previously we considered the square lattice, but one can also consider the like for example hexagonal lattice. So we'll consider elephant random walk on the faces of hexagonal lattice. So here the elephant has each step has 6 choices. So and one can view this work as a stable reinforcement work on Z2. How? So if this elephant moves to your right, it's equivalent to say that it made a step 2, 0. If you made a step to the right above, it's equivalent to saying that you made a step 1, 2. So this step is -1, 2. This step is -2, 0. So basically, you can view it as a stable reinforcement work, and the mu is uniform on the 6 directions. The alpha equals 2p minus 1 divided by 5. because of this equality. So the left-hand side is just the differential, the first differential elephant random walk. You choose a previous step and decide whether to repeat it. The right-hand side is just you using the language of stapling random walk. There is a parameter alpha. So with parameter alpha, we use one of the previous steps. Then, so we have shown that in dimension 2, there is a phase transition at alpha equals 1/2. You solve alpha equals 1/2. Then this gives us this result that this elephant random is recurrent if p is less than 7/12. Is transient if p is greater than or equal to 7/12. So actually, so 5/8 is a constant depending on the lattice. And if you change on the lattice, you change the lattice, you may give a different criticality. Okay, any questions so far before I talk a little bit about the proof?
You phrase the general result then for the type of lattice and depends on the constants of the lattice, or you just did that case?
Anyone? What? So basically, until now, most of the research on elephant random are focused on ZD. Yeah. So. Yeah. So yeah, this is for the hexagonal lattice is easy way to generalize this. But actually, from my perspective, the most natural way to generalize elephant random walk is considering elephant random walk on calligraphs. Because on calligraphs, you have a so-called generating state. Yeah. Then you considering so for each step, you considering how many steps you have made using the element, even the elements in the generating state. Yeah. But so far there is no paper on. So yeah. Maybe yeah. Okay. So let's talk about a little bit about the proof for the two-dimensional case. For subcritical regime, when alpha less than 1/2, I'm going to use the Lyapunov function method. But before in order to use this method, we need to have some control on the environment. For alpha greater than 1/2, we can consider the general stable random walk. We're using a connection to the population and random recursive tree. So the Lyapunov function method was developed by Lamberti. One of the typical arguments is like this. So here we're considering Markovian case. So imagine that we have a random walk on ZD. One useful way to show that it's recurrent is we try to find a good function f such that f goes to infinity if x goes to infinity, and the f of xn is somehow a super martingale, at least outside some fixed ball. Then by using martingale convergence theory, one can show that f of xn converge almost surely. But if xn never go back to the fixed ball, f of xn will diverge. So this shows that if you start from any point outside this ball, you will eventually come back to the ball or fixed radius. Actually, you will return to the fixed ball infinite many times. So this proves the recurrence for Markov chain. But one can, for two-dimensional simple random walk, one can simply take fx to be the square root of log x. Or using, if you know a little bit two-dimensional simple random, we can use the so-called potential kernel. Yeah.
Harmonic function?
Yeah, basically, if you're using a super martingale, yeah, but discrete super martingale, but it's very close to the super harmonic in R2. Yeah, in our case, for elephant random walk, one can actually show that for any vertex x in this lattice x, the next step is to one of its label y. The probability is lower bounded by some constant, some partial constant. Then you use the conditional Borel container lemma to conclude that on the event that x is very infinite many times, then almost surely y, so any of its labels y will also be weighted infinitely many times. So this shows that either all the vertices are weighted infinitely many times, or all the vertices are weighted finitely many times. So then we just like in this argument, we it serves to show that this elephant one will return to some fixed ball infinitely many times, or return to some fixed ball almost surely. So, but how can we? Sorry. So here, in Markovian case, it will be somehow easier to compute the left-hand side. But for non-Markovian case, the left-hand side does not depend only on the current projection xn. It also depends on the whole past. So we need to have some control on the past. Or here, we can view this elephant random walk as a random walk in dynamic environment. So basically, imagine that we're using the view of this particle. So we imagine that at the time n, we just stand at with the particle. Imagine let's say at time n, Sn is at vertex x. Then the next step is you choose one of the 4 directions. One can just assign weights to W to the corresponding H by using the corresponding jump probabilities. So this is the jump probability. Yeah. So then we update this environment, or local, actually essentially local environment at each time step. So then we want to have some control on this dynamic environment. So basically, we are going to show that the second term alpha times the empirical measure minus 1/4 is actually very small when alpha is less than 1/2. So this can be done by using stochastic approximation or using some result from polyar model. Actually, in dimension 2, it's equivalent to have a polyar for R model with 4 colors. At each time step, you draw a ball, you observe its color, you first put it back. With probability P, you add a new ball of the same color. With probability 1 minus P divided by 3, you add a ball from one of the 3 remaining colors. Then you somehow equivalent. The empirical distribution of the steps is equivalent to the empirical distribution of the balls of different colors. This result is somehow standard. When P is less than or equal to 5 or 8, or alpha is less than or equal to 1/2, the empirical, I will call this empirical measure, n of v divided by n, this empirical will convert to the uniform measure, 1/4, at the rate of 1 over square root of n, basically. Yeah. Then we can define a stopping time, tk. So actually, tk is the smallest time after time k that the empirical measure and the uniform measure there are a little bit difference between the empirical measure and the uniform measure 1/4. So actually, one can say that non-rigorous speaking, one can say that before. So we will start the process at time k. Before time tk, this work behaves very like just like a 2-dimensional simple random walk, because the local environment basically looks the same, or with some small errors. Yeah. Sorry. So the second term is actually very small. Now we can use the Lyapunov function method. So we first prove the weaker result. So instead of showing that this work will return to some fixed ball, almost surely, we first say that this will go back to a ball growing radius, a growing ball infinitely many times. So P less than 5 or 8 is just saying that alpha is less than 1/2. So one can choose a constant S which is greater than 1/2, or greater than alpha but less than 1/2. Then we show that so there is a growing ball into the or radius into the S. So eventually this ball will catch up with the particle, even if the particle starts at some position which is outside this ball. So the proof is that this. We define tau k to be the first time you return to the growing ball, and we just use the same Lyapunov function square root of log x. Then here one can just use entire expansion. Because the first moment and second moment of S of the conditional expression of Sn is easy to compute. The increments is easy to compute. Then one can show that this is non-positive. So basically, when alpha is non-negative, this term alpha divided by this is actually the force that push this elephant go to the infinity. But actually, we can have some estimate on this force. We can show that it's not that strong to push it to the infinity. So before this elephant returns to a growing ball, the denominator is somehow lower bounded. Until time n, the total for energy or the total influence on the force is actually upper bounded by the square root of S times log n. Of course, it's also bounded by this by the definition of tau k. So this shows that this is a super martingale, and it's actually is lower bounded because f. So indeed, f is the Lipschitz function. So here you have Sn, here you must have Sn minus 1. So it's a lower bounded super martingale, so it converges almost surely. This shows that f S of Sn is somehow upper bounded by this term. But S is less than 1/2, but it's actually impossible because of the law of iterative logarithm. So f of Sn is the limit soup of log of square root of log Sn is at least a square root of 1/2 times log n, because you use in the LIL. So the argument is that I guess if on the event that both tau k and tk are infinity, then this martingale, the super martingale, the limit soup is lower bounded by this. But we know that this term will convert has a limit soup, the square root of 1/2, which is greater than square root of S. So that shows. So basically, this forms pushing this particle, pushing the elephant to the to further away from the region is not strong enough. Using this force itself cannot make sure that it will reach the square root of log n, or square root of 1/2 times log n. So basically, then this shows that here we say for time k, but this argument for any k. So this shows that tau m, the minima of tau k and tk are almost surely finite. But we know that for large m or for large k, tk is infinite. So the only possibility is that there exists some tau m which is finite. But tau m is finite. This will show that tau k is finite by the definition of tau k. Okay, now we first show a weaker result, but this actually gave us a very so even it's a weaker result, but this gave us a very good initial condition. So for reinforced random walks, a good initial condition matters. So from the previous result, we can find the infinite sequence of nk such as snk, the norm of snk is bounded by nk to the s. And also by even previous lemma, we can find nk such that the distance between the empirical measure and the uniform measure is very close. It's there is one third, even less, even bigger than 1/4. Then start from time nk, we can define, now we define tau k to be the first time you return to a fixed ball. And theta k be the first time you going out, you reach a boundary of growing ball of n to the t. So this is almost finite because here we choose t to be a constant greater than s, but still less than 1/2. This is finite because the low iteration logarithm. Right. Then using Taylor expansion again, we can show that f of xn itself, before those stopping times, itself is a supermartingale. Now using argument just like a gambler's ruin. The initial condition is that make sure that it's less than square root of s times log nk. But on the event that you first reaching the boundary of the growing ball into the t, here the value of s is at least t log the square root of t times log of theta k, but theta k is greater than nk, so it's greater than this. So this shows that before time tau k and tk, here tk should be understood as tnk actually. Before this, the minimum of these two stopping times, if you want to reach the boundary of the growing ball into a t, you have to pay a price. So if you look at the simulation, no, that's not simulation. You look at the figure. Basically, you start from a point less than n to s. Then you want to reach the boundary of the n to the t. Before you return to the fixed ball of radius capital R, you have to pay a price. That is saying that this probability is bounded, has a probability bounded away from 1. But on the event that tau k and t, both tau k and tk are infinite, tau m and tm are both infinite, infinite. Then we just use previous result saying that it's bounded away from 1, and then we let m goes to infinity, use log with 0, 1, no. We actually will show that the event that both tau k and tk are infinite has probability 0. So just like before, the minimum of tau k and tk is almost sure finite, but tk for some k, tk is infinite. So this shows that tau k is almost surely finite. So they basically you return to some fixed ball almost surely. You repeat this argument, you return to the fixed ball infinite many times. How long has
Will you know the probability by constant that's more than 1?
Sorry?
About the probability that by constant is more than 1? The one on the
yeah. Yes. So
you can move.
I use this. You divide by both sides by square root of log nk. So this probability, here I put for k, but it actually works for any k. Okay. Yeah, so you divide it by square root of t, then this probability is bounded by the square root of, okay, so I just want to mention that Curry and Rollin has give a new proof for the recurrence for p less than 5 or 8. But they also have some control on the past or on environment, but they use they didn't use stochastic approximation. They use some kind of functional central limit theory. Then actually one can show that the law of the elephant random walk is absolutely continuous with respect to the simple random walk. They have some control on the and have some estimate on the random nicotine derivative. So for two-dimensional simple random walk, we have some lower bound for the returning probability within the next n step. Then once you have some estimate for the random nicotine derivative, we also have some lower bound for the returning probability for the elephant random walk within the next n steps. You return to the region. Okay. But one can, of course, one can try to use the Lyapunov function method to stable reinforcement work. But I just want to mention that there are a few things that are different. One thing is that for stable reinforcement work, basically to control the local environment, here we have infinitely many kind of steps, or it's somehow equivalent to saying that we have R with infinitely many colors. It's usually harder to show that the empirical measure convert to the uniform. The step distribution view. But there exists some result. For example, it was proved by Jensen, Miller, Wallace that have such a kind of convergence. And they also gave some estimate on the rate of convergence. But this for class of function G, but actually I improved a little bit on those assumptions. For a larger class of function G, we have this convergence. And also, previously we used the Taylor expansion, which it depends on the argument that the next jump is relatively small compared to the current distance to the origin of the norm Sn. But for stable reinforcement work, there exists some large jumps. So basically, one need to use truncation arguments. Because of the two reasons, so I impose the stronger assumption, 2 plus delta as moment assumption. But actually, once after I solved the recurrence transience problem for elephant analog, Professor Botois introduced me to the question of stable reinforcement work. So he even conjectured that a 2-dimensional stable reinforcement work is recurrent under for alpha less than 1/2 under the second moment assumption. So here I proved that this is true under 2 plus delta moment assumption. Let's quickly talk about the supercritical region. So it has a connection to the random reserve tree and the percolation. So here, let C be IID random variables with random variables with parameter alpha, and we let theta be IID mu distributed. So now we're building a random recursive tree. So initially we have a node 1. Then at each time step m, we add a node m and collect to one of the previous n-1 nodes uniform intrusion as its parent. So, right after you collect this new load, if Cm equals 0, you just delete this new edge. Otherwise, if Cm equals 1, you just keep this new edge. For fixed, you do this until time n. But for fixed n is somehow equivalent to saying that we first sample a random recursive tree and do a Bernoulli bound percolation with parameter alpha. But here we decide whether we keep or remove this new edge right after we add this new node, because in this case we can update this tree step by step. Otherwise, we need to resample the whole tree at time n plus 1. Okay, then at time n, then we're going to have several clusters, the collective components. Then for each component, the load with the smallest label is called its root. For example, this one is a node, but at node 2, there is no cluster rooted at 2. So we'll say that basically the cluster C2n is empty, but C1n is not empty. But C3n is not empty. But basically, this decides on whether Ci equals 0 or not. then one can show that the sum of the spins of the whole system defines stable reinforcement work with stable diffusion mu and parameter alpha. So basically, when you when Ci equals 0, it corresponding to the case that we sample independent step from mu. If Ci equals 1, basically for the I step is chosen from one of the previous steps. Actually, from this tree structure, the forest structure, we can even see which of the previous steps were was chosen. For example, at S step, it's just a copy of the second step. Okay. So now we're considering the case for alpha greater than 1/2. We have mentioned that for alpha greater than 1/2, if Sn divided by n to the alpha converts to some random vector W. Now we are interested in the distribution of W. So when we divide both sides by n to the alpha, so it's very we are interested in the growth rate of the cluster size. So it has been proved that
the CIN
is
are all the same for any n, basically.
For
fixed I, CIN
yes
has the same value over all n, because it is picked only once on the root.
Say for at time n there are several clusters, right?
Yes, but one cluster, the cluster of 1,
yes,
has one value for C1, whatever.
Yes, yeah, all of them, yeah. So for example, at time n equals 8, then 1, 2, 8 has the same spin,
yes,
has Cc1. No, theta 1, sorry. Yeah,
Okay.
yeah. Basically, each cluster have the same value or the same spin. Because it's a copy of the past. Yeah. Now, given that there is a cluster at node I, then the cluster rooted at I grows as n to the alpha. So basically, the cluster size divided n to the alpha convert to some positive limit. So then there will be under the assumption that under a second moment assumption, basically. So basically, using argument from Bourtois that here we can divide it by both sides by n to the alpha, and we can put the n to alpha inside the limit sign and the summation sign. So here you divide by the cluster size by n to the alpha, which will give you 1 minus Ci. 1 minus Ci decide whether it's empty or not, times rho I. Basically, we can put n to the alpha inside this summation. Let's convert Sn divided by n to alpha convert to W in L2. So this gives an expression for W. Then we need to show that W, we want to show that W is almost surely non-zero. Then we can prove a general result that because of the previous result, the coefficient in front of theta I is almost surely is a L2 sequence. And it has infinitely many non-zero terms. Then we can show that if for such a random series, almost surely it's continuous or non-atomic. So I'm not going to prove this, but we can look at a simpler example for the one-dimensional elephant network. This corresponds to case mu is actually a Rademacher distribution. So we say theta n is a Rademacher series if it takes values in -1 and +1 with equal probability 1/2. Then the previous proposition it becomes this. So basically the same assumption. But how one can prove this? This is somehow a well-known property for Rademacher series. Let's argue by contradiction that there exists some x such that the r dot theta equals x has positive probability. Then because of something on R, it's L2 sequence, and so it's converted to 0. Then we can find the infinite subsequence Rnk, such as the absolute value of Rnk strictly decreasing in K. Then the inner product belongs to this set equals this probability because the values Rnk are distinct. But now we compare these two probabilities. So here, so we're considering theta. If we replace theta nk by minus theta nk, and all the other elements remains unchanged. This basically this does not affect the distribution of theta. So, but if R times theta equals x, then this will give that R theta tilde belongs to x either plus or minus R nk. This shows that this probability is lower bounded by this probability. It's clear? So this will, but this will equals the summation equals infinity. This is a contradiction. But for the previous general is that the proof is a little bit more complicated. But the basic strategy is also using a certain kind of coupling. Yeah, you use you introduce two sequences of data that have the same distribution. Yeah, I don't know whether I believe there should be even general with that. yeah. So, yeah, that's the result is on standard. So I just want to lastly I want to mention that for this is for stable infrared work, but actually for elephant work I use a different method, but I don't have time to explain here. Using a different kind of method, one can even show that for example for one-dimensional elephant work, the limit W1 has a the distribution of W1 has a density. It's stronger than saying that it's non-atomic, and the support of the density is on the whole real line. So this was proved by Guerin, Lorraine, and Russell independently. They even show that the distribution of W1 and W2 and W3 all have a density. Yeah. Okay, let me summarize. So PD, we define PD as a critical parameter for elephant network in dimension D. When in dimension 1 equals 3/4, in dimension 2 equals 5 or 8. When we show that in dimension 1 and dimension 2, there is a phase transition between recurrence and transience. But there are a little bit difference between dimension 1 and dimension 2 at criticality. And in higher dimension, for any parameter P, it's always transient. Then actually we can also observe a phase transition of the angular component at any dimension D. It occurs at P equals PD. So if P greater than PD, there is a limiting direction. Otherwise, almost surely there is no limiting direction. Then we generalize those results to the stable infrared work. Then we see that actually, okay, 5 already is an interesting number. So 5 is a lucky number for my PhD advisor. But 8 is a lucky number in China. But we said this parameter PD, it depends not only on the dimension, but also on the lattice. But if we view it as a stable infrared work, one see that there is a unipole criticality at alpha equals 1/2. This is independent of dimension and independent of basically lattice. Okay, thank you.
Thank you. Very nice talk. In view of time, maybe one question.
Say anything about like null recurrence or positive recurrence?
So I think for in higher dimension, for dimension 3, because they are all transient, so there's no need to talk about recurrence, right? In dimension 2, so we only need to consider the case when p is less than 5 or 8. Actually, there's up to now there is no result on that, but as for it should be. Okay, I'm not saying that is trivial, but I guess for at least for p greater than 1/4, because simple for two-dimensional simple random walk is non-recurrent, right? I think for p greater than 1/4 is even more transient, but it's still recurrent. So I believe that it's still non-recurrent. But for I also believe that for p less than 1/4 is also non-recurrent. But now I don't have a proof for that. Yeah. But sorry. For I didn't mention that in dimension 1, Bourtois proves that in his paper, counting zeros of elephant random walk, they prove that in dimension 1, it's positively recurrent if and only if p is less than 1/6 in dimension 1. This is, in dimension 1 there is no, but in dimension 2 there is no result. Yeah.
In the tangent case, I think you can about long tangent, I mean the conditional on the return time infinite, expectation infinite.
Yeah. So I actually in my paper I prove that the expected number of returns is finite. But I didn't. That's different from the expected return times, right? But expected return time is infinite, right?
No, conditional on the event that return time is finite. There is expectation is finite.
Okay.
The expectation of return time given is finite.
Given is finite. Okay. Okay.
Definition for job tangent.
Okay.
I think in dimension 4, it's with tangent for simple random walk, but
okay. Okay. Good question. Sorry.
There will be coffee, Jake.
Okay. Thank you.
Speak again.